Hello everybody, and welcome to week 6 of Math 196. In this presentation I'll be covering compound and continuously compounding interest. This is a continuation of material you learned in section 2.5. In addition to compound and continuously compounding interest, we will be looking at how to determine the growth rate and the amount of time required to reach a desired amount. The first thing that we should address is there is a new formula introduced in this chapter. The new formula is A equals P times 1 plus I to the n. I and n are both new to you, but luckily they come directly from the formula you already know. N is the total number of compounding periods, which is the same as m times t, and then I is the rate per compounding period, which is the same as R over M. Now if you plug both M and T and R and M back into this formula, you get the same one that you already know. You will need to use both formulas in order to do your homework, so please don't be surprised when you see I and N show up. Now let's work on a couple examples. We'll use these later in this presentation in order to look at how to compare different investments. Suppose you have $2,000 that you are going to invest at an annual rate of 8%. After 5 years, what is the amount if the interest is compounded quarterly and if it is compounded monthly? First, we need to pull the variables from the problem. For our value of P, we get 2,000. R is 0.08. The first value of M is 4. The second value is 12. And T is 5. Taking those values and plugging them into the equation for the quarterly, we get 2,000 times 1 plus 0.08 over 4, all raised to 4 times 5. We simplify all that to get 2,000 times 1.02 to the 20th, and that yields an amount of $2,971.89. Now to figure out the compounding formula, we do the same thing. We have pulled the variables out. This time we're looking at the second value of M equals 12, plugging those in and simplifying, we get 2,000 times 1.0667 to the 60th. This we can plug directly into our calculators to get $2,979.69. The next portion of the chapter goes over continuously compounding interest. This is exactly the same as what you were shown in 2.5. It is A equals P to the ERT, or P times E to the RT. With that, let's look at an example for this one. Notice we are going to be using the same values for T and R and P for this. That way we can go back and compare these a little bit easier. So you are going to invest $2,000 for 5 years at a rate of 8%, but it is going to be compounded continuously. What will your total be? Pulling the variables from this problem, we get P equals 2,000, R is 0.08, and T is 5. Plugging those values into the equation, we get this, and then simplifying that, we get 2,000 times e to the 0.4, which yields a final amount of $2,983.14. Now let's compare these accounts. Which of the three investments is best? Just from looking at what we got for final amounts, the third option is the best. It has the greatest total amount in the end. It's very straightforward. But the third party also has one thing, or the third investment has one thing different from the rest. They all started with the same principal, interest, and amount of time invested. The reason why they are different is the number of times interest was compounded. It really matters. The continuously compounding, it was compounded the most times. If how often we compound interest matters, along with the rate and the length of time required for an investment to mature, how do we easily compare each of the investments to figure out which one's better? The long way is plugging in the numbers, or we have another measurement called annual percent yield. Annual percent yield, or APY, is the interest rate required to have a simple interest problem that yields the exact same amount after 1 year. By standardizing the result to just 1 year and having the simple interest charged, it gives you a uniform measure for each of the investments to be compared. Just a simple reminder, simple interest is the same as A equals P times R times T. Using APY, we have two different formulas, one for compounding interest and one for continuously compounding interest. For compound interest, the formula is 1 plus R over M raised to the M minus 1. Continuously compounding interest has a simple formula as well of E to the R minus 1. So let's look again at these examples and see if the answer that we got just looking at the amounts is also shown in the APY. We will be using these formulas to figure out the APY from each of the examples, plugging in the values of R and M into the formula for APY. We get 0.08243 for the first interest rate. APY2, or for the second example, we plug in an R of 0.08, M of 12, and we get a value of 0.08300. So far this is making sense. The second example had the second highest amount. So the third example, if it's the same, it should be higher than the previous two. And just looking here it is. We plugged R into the equation and we got a result of 0.08329, which is a higher interest rate, which is the highest interest rate of the three. So again, the APY tells us the simple interest that is required to get the same result as our original investments. Just like when we looked at the final results, the APY of the third example is the best option and would require the highest simple interest rate to achieve the same results. The other types of problems to be expected from this section of the book is a problem how to determine growth rate or the amount of time required to reach a given value of A with an initial value of P. The first example will be finding the growth rate. You just graduated college and you want to save up for a brand new car. You have $1,000 to invest and you would like to purchase the vehicle within the next 5 years. The car you want costs $25,000 and you need to have a 10% down payment. What is the minimum interest rate you need in order to make your goal? Assume interest is compounded monthly. Pulling out the values we need to satisfy the equation for compound interest, we get P is 2,500. I got this, or A, not P. The amount that we need at the end is 2,500. This is 25,000 times 10%, because that is what we actually need in order to make the purchase. P, or the principal required that we have, is $1,000. R is what we're solving for, so I'm going to just say that's X. M is 12, and T, the time that we need this by, is in 5 years. Plugging these values in, we get 2,500 equals 1,000 times 1 plus x over 12 raised to 12 times 5. And then the rest of this work is going to be continued on the next slide. So now we need to solve for x. We had a 1,000 here. What I did is divided both sides by 1,000. and I simplified the 12 times 5 to be 60. Taking this to the next step, I divided 2,500 by 1,000 to get 2.5, and then we take the log of both sides. From there, we use the log rule. We pull the 60 out in front because it's an exponent. And then we divide by 60 on both sides. Now, this 1 over 60 is that is a constant being multiplied by a log, so that can be brought inside to be 2.5 to the 1 over 60th power, and that equals the log on the other side. Now, we have logs on both sides. You can think of that as canceling. The real process that we're doing is raising 10 to the power of each side, which will cancel out the logs. So we have 2.5 to the 1 over 60th equals 1 plus x over 12. We bring 1 over to the other side by subtracting, and then we multiply both sides by 12 to get x completely by itself, and that leaves us with an interest rate of 18.47%, or if that's a decimal, 0.1847. So the last type of problem that you'll be seeing in your homework is a problem asking you to solve for the growth time required. For this example, the national average for high yield savings account is about 0.1%. You have $5,000, and like me, you want to be a millionaire. How long will it take your $5,000 to become 1 million in an average high yield savings account that compounds interest every week? Pulling out values we need for the equation, we get A equals P times 1 plus R over M to the MT. So A is going to be 1 million, that is the amount we want. P is $5,000, the amount that we have. 0.001 is the interest rate. M is 52, and T is X, which we're going to be solving for. Plug those in to get this formula. Again, the work is going to be shown on the next slide. The first step will be simplifying whatever we can. So, again, we have 1 million equals 1,000 times 1 plus 0.001 over 52 raised to the 52x. Dividing both sides by 1,000, we get just 1,000 on the left, and on the right we have this large formula for the interest. So we take the log of both sides. The log of 1,000 equals the log of 1 plus 0.001 over 52 raised to 52 times x. This 52 times x is an exponent inside a log. We can take that out so that it is being multiplied to the log on the outside. Now both 52 and everything in the log are just being multiplied to x. We want to get x by itself, so we divide all of this on both sides, and we get x equals the log of 1,000 divided by the log of 1 plus 0.001 over 52 times 52. And that will give us the number of years required to become a millionaire off of $5,000. And I hope you live that long, although I sincerely doubt it.